Welcome everyone. In this video, I'll walk you through the different GPU architectures produced by Nvidia. Let's start with the shown image. This image demonstrates that Nvidia has launched numerous architectures since 1998. However, we will skip over some of the earlier architectures as they are no longer in use. And we are going to start our exploration with the Fermi architecture that Nvidia brought out to the market in 2010. The shown table presents all architectures introduced by Nvidia since 2010. First, I'll explain each column before delving into the architecture's details. The first column shows the architecture name that Nvidia has introduced. The second column shows their corresponding release dates. Then we have the GPU chip example column. This column offers a representative electronic chip of each architecture. As we proceed, I'll highlight two distinct GPU models for each architecture. These are categorized in two columns. The first one is the HPC GPUs, or the high performance computing GPUs. And the second one is for the non-high performance computing GPUs, which means the GPUs that are designed for general users or general consumers. Lastly, we have two additional columns dedicated to assessing the computational power or performance metrics of each architecture. In this table, I have selected only two key parameters for this comparison. The first one is the throughput, which calculates the number of floating point operations per second, and the second one is the clock speed. For these parameters, in most cases, I'll show one value for the high-performance computing GPU and another for the GPU dedicated to regular consumers. Now, I'll delve into the various architectures of Nvidia GPUs. Let's start with the Fermi architecture. The Fermi architecture introduced by Nvidia in 2010, and it was a significant leap in GPU design and technology. Fermi-based GPUs were produced using 40 nanometers technology. An example of a GPU chip that is based on the Fermi architecture is the GF100 chip. This chip is used for producing many GPUs for the purpose of high-performance computing and also for the regular users or the regular consumers. For example, one of the high-performance computing GPUs that is based on this chip or this architecture is the Tesla X2070 or X2070. On the other hand, the GeForce GTX 480 is designed for general consumers and gamers. In terms of performance metrics, these two GPUs could achieve a throughput of 1.2 and 1.3 teraflops with a clock speed of 655 and 701 MHz respectively. Now, if you focus on these numbers, the performance metrics numbers, you might question why the GTX 480, which is designed for regular users, exhibits superior performance compared to the X2070 GPU. For example, the GTX 480 has a clock speed of 700, while the X2070 GPU stands at only 651. To address this, it's essential to understand that evaluating GPU performance isn't straightforward. A singular metric like the teraflops or the clock speed is not enough to assess the overall GPU capability. The total performance of a GPU is influenced by multiple factors and metrics, not just these two metrics. Furthermore, what seems beneficial in one metric might be detrimental in another context. For example, while a higher clock speed might accelerate tasks, it could also lead to increasing the power and energy consumption, which may not be desirable for specific systems. Additionally, it's important to clarify that the teraflops value or the throughput value for the GTX GPU, which appears superior to the X2070 GPU, is specific to the single precision operations. This is not for the overall cores in the GPUs. Let's take an example to illustrate this in depth. When we open the Tech PowerUp website for both GPUs, you will notice that the double precision performance of the X2070 GPU, as shown here in this part, is around 582 gigaflops. This value is higher than the value of the GTX GPU. The GTX 480 GPU has only 168 gigaflops. This indicates that the X2070 GPU outperforms the GTX GPU by a factor of nearly 4 when it comes to the double precision tasks, and one of these tasks is the scientific simulation. However, in texture and pixel rate metrics, in which the single precision operations are required, the GTX 480 GPU has the edge over the X2070 GPU, and this aligns with its intended use for graphics, gaming, and everyday activities. Let's return to the PowerPoint to explain the next architecture, the Kepler. 2 years following the Fermi release, Nvidia launched the Kepler architecture. Observing this column, it becomes clear that Nvidia has a pattern of releasing a new architecture roughly every 1 or 2 years. The Kepler architecture is manufactured by the 28 nanometers technology compared to the 40 nanometers technology used with the Fermi architecture. The Nvidia GK210 chip is primarily known for being used with the Tesla K80 GPU. This GPU is a high-performance computing GPU card. Surprisingly, the Tesla K80 GPU consists of 2 chips, not one. So, on a single board, two GK210 chips are used. With the 2 chips combined on a single board, the K80 GPU achieves a throughput of approximately 8.2 teraflops. This is a 6 times increase compared to the Fermi architecture. However, it's essential to note that this throughput value includes both chips. This means that each chip or each GK210 chip delivers roughly 4.1 teraflops. Beyond the K80 GPU, there aren't many widely known GPUs based specifically on this chip. Most of the other Kepler GPUs for the consumer market were based on different chips. For a more extensive list of GPUs based on various Fermi chips, you can refer to the Fermi section on the Tech PowerUp website. The last thing that I want to mention about Kepler is the upgrade. Sometimes Nvidia releases an upgrade or another enhanced version of the same architecture. For example, Kepler was first launched by Nvidia in 2012, but between 2013 and 2015, newer versions of Kepler emerged, as indicated here in this image. You can observe that the same thing happened with the Maxwell architecture. This is why when you open the Tech PowerUp website to look at the GK210 chip, you will find that it was released in 2014, which differs from the 2012 provided in the table. The release date in the table is for the first version of this architecture. The Maxwell architecture, which is introduced by Nvidia in 2014, was a significant advancement in the field of GPUs. It also manufactured by the 28 nanometer technology. One of the flagship chips of this architecture is the GM200. This chip was incorporated into the Tesla M60 GPU, which is designed specifically for high-performance computing. Additionally, for those interested in gaming, the GeForce GTX 980 Ti is another GPU that is based on the Maxwell architecture. Regarding the throughput, the M60 delivers 9.7 teraflops, where the GTX GPU delivers 6.1 teraflops. In terms of clock speed or frequency, the M60 operates at 557 MHz, while the GTX reaches 1000 MHz. Again, the M60 here that is dedicated for the high performance computations has lower clock speed, which is directly related to the energy consumption. Okay, so starting with the Pascal architecture, the high-performance computing GPU cards have adopted a naming pattern that includes a letter followed with 100. Thus, in Pascal's architecture, the GPU name is P100, where P refers to Pascal. This trend continues with Volta, Ampere, and Hopper. They are labeled as V100, A100, and H100. This naming approach is mirrored in the GPU chips too. As we see, we have in Pascal GP100, and then in Volta, Ampere, and Hopper we have GV100, GA100, and GH100. The Pascal architecture, which is introduced in 2016, is manufactured by 16 or 14 nanometers technologies. So, you might wonder, why do we have two different technologies in the same architecture? It's primarily because various manufacturers in the market had access to different levels of technology at that time. While some could produce GPUs using the more advanced 14 nanometers technology, other companies still working with the 16 nanometers process. Despite these differences, each company was able to produce GPUs based on the same Pascal architecture but with varying nanometer sizes. Okay, now I'm not going to talk too much about the Pascal architecture because I'll explain it with the remaining architectures from the white papers or their datasheets. Just one thing here, as we see, we witness remarkable advancements. Just look at the throughput of the Hopper architecture and compare it with the Fermi values. That explains everything. From 1.2 teraflops in the Fermi architecture, we have now 378 teraflops in the Hopper architecture. I am skipping the 51 teraflops written here because it will be explained in depth in the Hopper architecture video.